Uh, Welcome everyone. This week's QTFM seminar, we host Alex Kamenev from University of Minnesota. He's going to talk about quantum algorithms for optimization and AI training. So if you ready, you may start.
All right. Yeah. First of all, thanks for invitation. It's a great pleasure to be with you. Yeah, and please interrupt me anytime you have any questions. It should be completely informal. So I want to tell you a little bit of our thoughts and attempts to do quantum algorithms and implement them at existing quantum devices. So will tell you exactly what I mean by that and how it works. So motivation comes from the fact that various smart people and companies invest quite a bit of effort lately to create quantum prototype typical quantum computers or devices, whatever you call them. So here is Google. There are many friends of mine working for them. So it's a superconducting computers. IBM is quite similar. I will tell you mostly about my work with D-Wave machine, and I will tell you exactly what they have. We also work with Quantinuum, which is very different. They use cold atoms, and we work a little bit with them too, but today I will practically not talk about it. So if you have questions, I may be able to answer, but I will not give you many details of that. All right, so yeah, let me start from a very basic. So the idea behind quantum computer is that instead of usual classical bit, which is 0 or 1, one can use a quantum state to quantum two-level system, which is characterized by a Bloch sphere. So the state of a quantum system, of two-level quantum system, is characterized by a position on a sphere. Any point on the sphere represents a distinct quantum state. So you can read in popular literature that that's what gives quantum computer an advantage, because instead of discrete information, it has this continuum of possible states. Now, that's totally nonsense. That's not what is important about quantum computer. If you want a state on a sphere, just take a classical needle compass, three-dimensional compass arrow, and play with many three-dimensional magnets, and you will have states on a sphere. So that's not what makes quantum computer promising object. What is the fact that if you have two qubits, now you have four possible states, but if you have, which is pretty much equivalent to two magnets, classical magnets. But if you have three, now you have eight, and if you have n, you have 2 to the power n. Not 3n, but 2 to the power n. And this exponential largeness of the Hilbert space, which sometimes is called entanglement, which is pretty much meaningless word, but the exponential largeness of the Hilbert space of n quantum systems, qubits, that's what in principle can give you an advantage of doing something which classical computer cannot do. Because with classical computers, everything goes kind of linearly with a number of available bits. Here, in principle, things goes exponentially. Okay, it's a big question how to use this exponential largeness, and it's far from being clear that we can do it, but that's what these people are trying to do. And I will give you specific examples how exactly we try to harvest this exponential largeness of available Hilbert space. Yeah, please, but again, please interrupt me if I'm too slow, too fast. Now, there are roughly two competing paradigms in quantum computation, which sometimes go by the name of gate computers versus annealers. So the gate computers supposed to operate pretty much like our conventional computers. You have a set of bits. Actually, let me try to do my laser pointer. How do I do it? Yeah. Okay, I will use my arrow. So the gate computer is supposed to operate in a set of qubits, and you do single qubit operations, and then you do two qubit operations, and then keep doing like a conventional code of any computer program you write is working. So that what many people hope to be doing with the quantum computers, and it's not clear if they will ever be successful doing it. The opposing kind of line of thoughts is that they can create a quantum system, so many qubits interacting in a certain way, and then let them evolve according to whatever quantum Hamiltonian or quantum evolution operator which governs their evolution, let them do whatever they want, maybe interfere with some, comments and changing some parameters in a time-dependent way, but otherwise let them evolve according to the rules of quantum mechanics, and then in the end of the day do some kind of a measurement, extract some information, and hope that this quantum information is useful, has a useful part, which we can use for some task, solving some task. So these two groups are pretty much hostile to each other, or relatively hostile. I will mostly talk about annealing. Oops. Where is it? Yes, right. I will mostly talk about annealing things. So the pros and cons of these two strategies. So the gate computers look very promising, but as of today, none of them has more than 100 qubits. And probably the most significant handicap of them is that there are no proven algorithms which make them obviously superior to classical computer. The two exceptions are Shor algorithm for factorization and Groover algorithm for sorting the massive, but nobody was able to demonstrate them working in any sort of reasonable size problem. So factorization, they can factorize only very, very small numbers, which is of course not interesting at all. On the other hand, annealers can be much bigger. So today we have more than 5,000 qubits. That's this D-wave machine, which I will be talking about. And it's less versatile. It tailor-made to do specific, very specific tasks. It's not for universal at all. But these specific tasks can be quite interesting and quite challenging and for conventional computers. And in my opinion, if quantum computation will ever work, it will work in this right part of the screen for the problems like optimization, image recognition, training of neural networks, artificial intelligence. In short, problems which do not require unique mathematically exact solution, like factorization. Factorization has unique mathematically precise solution, and that's hardly achievable with quantum devices. On the other hand, tasks like optimization or image recognition, which philosophy behind which is let's find good enough solution, not necessarily the best, but just good enough. That what probabilistic quantum devices are good in solving, and I'll give you an examples. Yep. Are there any questions? Say something, because I don't know if I'm talking to people or to my computer. Hello?
Everything is clear so far. Everything
Okay.
clear.
All right. Okay. At least now I know that somebody is listening to me. Thank you. Okay. So let me tell you a little bit about optimization. So what is optimization problem? It's a classical problem. There is nothing quantum about it. So you want to find a set of zeros and ones, or I will call it ones and minus ones, just to make analogy with quantum spin. And this string of length n should minimize certain cost function. And that may be optimization of your investment portfolio. It may be optimization how to move containers through a port, or it may be optimization how to guide missiles, or whatever you want. So there is a certain cost function which you want to reach a minimum or maximum value. So the simplest one, which is very, very familiar for physicists, is just a binary products of various spins. So let me call it spin for the physics audience. But that's just plus minus ones. So we call it sigma z. So that kind of very much simplified cost function already very, very non-trivial. And it actually can model much more complicated situations and cost functions. So that I'll talk more when I will talk about D-wave. So a couple of famous examples. If Jij is just coupling matrix, Jij is just a random matrix taken out of some ensemble, that's a famous Sherrington-Kirkpatrick model, which brought Nobel Prize of 2021 for Giorgio Parisi. Now, in reality, it's not all-to-all interactions. So in reality, these qubits are packed in a certain lattice in three-dimensional space. So Jij is more or less random, but restricted to some d-dimensional lattice. And that's a problem of d-dimensional spin glass. And this problem is finding ground state of d-dimensional spin glass is known to be NP hard for d larger than 2. That means that it's pretty much proven that you cannot find ground state in a polynomial time, never mind classical or quantum computation, but you will not be able to find ground state in a polynomial time if dimensionality of this lattice is larger than 2. Okay. Now,
can I just
yes, absolutely.
So for D equal to 1 or 2, this is not NP hard, like one can find the ground state in a.
Yeah, in D equal 1, it's completely trivial. You just start on the left and you put each next spin according to, if connection is positive, you
Right.
put it.
Okay.
Right.
Okay.
So in D equal 2, it's much less obvious, but there is a proven algorithm which can find ground state in 2 dimension in polynomial time.
Okay.
I believe it was invented by Michael Fisher, actually, but I'm a little bit uncertain about it. But it is known. Now, if you have already 2 layers of 2-dimensional system, just kind of ladder, two planes, it immediately becomes NP hard.
Great. Okay, thank you.
Not at all. All right. So in principle, the problem is very simple. You just try all the combinations of plus minus ones, and you calculate corresponding cost function or energy, as we call it, and you find the smallest one. So the problem is that there are 2 to the power n distinct combinations, so you will need exponentially long time to try all of them. Now, that's of course not the best way of doing it. So what people do typically is what is known as classical annealing. Namely, you start from some random configuration or almost random, and then you flip one spin and you calculate energy. And if you find that it's less than the initial one, then you accept new configuration, then flip another spin at random. Again, calculate energy. If it's less, then you accept. If it's larger, then you reject. And you hope that doing it many times, step by step, you will be systematically go lower and lower in energy and eventually find your ground state. Now, that unfortunately doesn't work. And it worked by the reason that the energy landscape of those systems is what we call glossy. It's like a glass. Namely, in an energy landscape, as a function of some generalized coordinate, this is of course multidimensional space, but this is one-dimensional cartoon of this multidimensional space. So the energy landscape has many minima, and if you will do what I described above, more likely than not, you will be trapped in some minima. So a flip of any one spin will not lower the energy, but nevertheless, you will be sitting here and very far away from the true minima here, true ground state. Okay, so that is more or less definition of a glass, a system whose configuration space admits a lot of exponentially many local minimas.
Sorry
Now,
for
yeah,
I'm really sorry for interrupting you.
absolutely.
The algorithm you mentioned doesn't converges. I
Well,
mean, whenever you flip, I'm not sure. I'm just questioning. Would it converge to a specific point and decreases with time?
yeah, it will converge to a certain state. Namely, you try to flip any spin and you
Okay.
always go up in energy. Okay, so in that sense, algorithm converged. So you find a state which doesn't go down no matter what spin you flip. Okay, but it's still not a true ground state. It's still a local minima, because if you flip 55 spins, then you can find a better minima.
I see.
Okay.
Thank you. Thank you.
And finding which 55 spins you want to flip will require exponentially many,
Trials.
possibilities.
Yes.
Tries, right? Okay.
Thank
So
you.
that's the problem with classical annealing. Okay.
Thank you so much.
Now, the idea is to make the problem quantum. Now, what means make problem, in a kind of popular way? If you have this energy landscape and you trap in this minima, so classically you cannot get out of it. But if you have quantum mechanics, you may have tunneling, and then your system can somehow find a way from here to a better minimum here. Okay. Now, how to do it? How to make it quantum? So quantum means that you have terms in your Hamiltonian or cost function which do not commute with each other, like in Schrödinger equation, coordinate and momentum do not commute. So here we deal with spin problem. So in quantum mechanics, in addition to sigma z, so the spin glass Hamiltonian, it has only sigma z's. So we want to add something which doesn't commute with sigma z. So for example, sigma x, right? So the very simplest cartoonish example of it is that let's add magnetic field in x direction. Okay, so we have our spin glass, and now let's put it in a certain magnetic field which is directed orthogonal to my z direction. Now, then the thinking is like this. Suppose this X magnetic field is a very, very, very large. So if it is, then I basically know what is the ground state of my system. It's a state where all spins are looking in X direction, directed along the magnetic field. So this is a unique ground state, and it is gapped. So the excited states, you need to flip at least one spin. That will cost you finite energy. So you can easily prepare your system in this ground state in presence of a very large magnetic field. So here it is. So the vertical axis here is energy or cost. And then there are 2 to the power n, many microscopic states of this system. And we want to find the lowest one here. And we have no idea what it is. But if we have a very large magnetic field in x direction, then we do know what's the ground state. It's this simple state that everybody look in x direction. Okay, so I will initialize my device in this state in the presence of x magnetic field. And then what I will do, I will, in a time-dependent way, I will slowly decrease magnetic field. And then, according to our adiabatic theorem, my quantum system will follow this state. It will keep staying in a lowest state. And in the end of the day, it will slowly arrive to the ground state of the system, which I do want to study with zero magnetic field. Right? So that looks very good. So you just prepare it here, you decrease magnetic field, and you arrive to the state which you are looking for. You do measurement, and you find it. Now, that, of course, doesn't work because those levels exhibit tons of almost level crossing. And if you really want to do what I described, you will have to move along this line exponentially slowly. If you don't go exponentially slow, then you will necessarily have what is called Landau-Zener transitions, and you will find yourself in a superposition of ground state and many excited states. So then when you will do a measurement, you will find something which may be very far away from the state you're looking for. Okay, so only for exponentially slow protocol, this idea truly works. But if it is exponentially slow, then it will take exponentially long time. Then it's just better to try all 2 to the power n possibilities, and you don't need any quantum device at all. So that's a nice idea, but strictly speaking, it's not going to work because it's never going to be truly adiabatic. It will always have this Landau-Zener transitions. Is it clear?
Yes, sir, it's clear so far.
Okay, very good. So there are better ways of doing it. Namely, you should sort of think about it as a cooling, because finding a low energy state of a certain Hamiltonian means, or ideally ground state of a certain Hamiltonian, means that you want to prepare your system in a very cold, maybe even zero temperature ground state. Okay, so now how would you cool a quantum system? It's like pretty much a way you cool your classical system, your kitchen fridge. You do something in cycles, namely you have a working substance, in our case it's system of spins, and you want to drive it from a series of a phase transition. So here we have a freon in a fridge, which you compress and then evaporate and then compress again and then again evaporate. And one of these transitions is endothermal, another exothermal. And you want to arrange it in a way, sequence of this transition to cool an interior of the fridge and to heat an exterior of the fridge. So pretty much the same logic can work here. You can arrange a cycle. You need more than just X magnetic field. You need some extra time-dependent parameters. And you have quite a big bit of freedom how to choose them. So we have our sort of favorite way of doing it. I will not go into details. So you have X magnetic field and you have Z magnetic field chosen in a certain way. And you can arrange a cycle in a way to cross first order phase transition and second order phase transitions such that the end point of the cycle will be state which is almost surely have smaller energy than the initial state. So then you do a measurement, you find a state you like, and then you reinitialize your system and do the next cycle, and then you do a measurement. If you like the state, you again do something with your system and keep doing it. So that's a sort of schematic idea how we do it.
Question?
Can I ask?
Sure.
Sorry, Omar, you have a question.
Thank you. Actually, I have a question about this phase transition points. We
Sure.
are just have some cycle. So is there any coincidence that we are just crossing these lines, or just are there some intuition behind it?
Say again, is there any what?
Intuition behind it. For example, is this coincidental or just?
Yeah, no, there is quite a bit of intuition about it. But I don't want to go into details because that will take entire talk. If I will try to explain intuition, and there is no theory. Let me put it this way. So there is no detailed mathematical theory, but there is quite a bit of intuition why it is a good idea. Okay. Now it is published here and explained quite well, I believe. And if you have, questions how exactly it is arranged and what's the intuition, we can talk later privately. But I don't want to go to spend too much time on it.
Thank you. It will be great. Okay, thank you.
Okay, so contact me sort of privately or stay after the talk, and I can try to explain. Right. So I as opposed to doing that, I want to, since we don't have, as I said, we don't have detailed theory anyway, so we do experiment and we try to understand experimentally if this intuition, which I didn't articulate, is working or not. So now I'm coming to experimental part of my talk. So we use this D-wave machine. So the D-wave machine has 5,627 qubits. We now have a slightly newer version of it. It has a little bit 5,000, but they're better. So it's not the latest generation. It's next to last generation of this machine. Now, this 5,000 qubits, they have that many 40,000 connections, elements of Jij matrix, out of whatever, 25 million. They only have 40,000, which we can make non-zero. That means that each qubit is, so that's more or less sort of artistic vision how they arranged. So each qubit is coupled to about 16 neighbors, which is nearest neighbor and next nearest neighbor. So you can try to, so you have a piece of three-dimensional spin glass. It's 20 times 22 times 12, I believe, the size of this piece of three-dimensional spin glass, which give you roughly 5,000 qubits. So you can choose that many JIJs at will, and then you can play with magnetic fields in Z direction and X direction with any time-dependent protocol you want. And we want specific cycle protocol, which I briefly told you about. Now, what do we know? So as I mentioned, three-dimensional spin glass is NP hard. So here is a reference which proved it. Somebody asked me about it. You can go there and read details. Now, so it's non-polynomial, but still we don't know. It's not obvious what is a complexity. Now, for Sherrington-Kirkpatrick model, the best mathematical estimate which exists today, that if you have a quantum computer, you will be able to solve it with time, which scales like 2 to the power roughly n over 5. Okay, that's for Sherrington-Kirkpatrick, namely all-to-all, if you want infinite dimensional spin glass. Now, for three-dimensional spin glass, there is a mathematical theorem that complexity is larger than 2 to the power n to the power 2/3. So it's not exponential in n, it's exponential with n to the power 2/3. Basically, surface complexity is exponent of the surface area as opposed to a volume. And it's sort of relatively easy to understand why it should be surface area and not the volume. So that's sort of mathematical knowledge about expected complexity of computational complexity of the spin glasses. Okay, so now what we do with, yes.
Why is it easy to see that it should scale as the surface area? I mean, again, if that's not too much. So,
well, roughly speaking, is this. Suppose you have a cube, right? Of certain size n. Now you can take 3 orthogonal planes and cut it in x, y, and z directions into 8 cubes of size L over 2. Okay? If you have cube L times L times L with 3 planes, you can cut it into 8 cubes of size L over 2.
okay.
Okay? Now, then what you can do, you can fix boundary conditions, namely spin positions of all the spins along these 3 cutting planes. Okay? That will have pretty much that many ways of fixing these boundary conditions. Right? Now, once you fix it, if it's a short-range spin glass, then you can solve each of these 8 cubes independently with a fixed boundary condition. Now, how would you solve each of these smaller cubes? You again cut them into 8 cubes, each one of them cut in 8 cubes. And then each one of the smaller cubes you again cut in 3 free planes, and so on and so forth. So you can have this iterative procedure, and it's pretty easy to show that overall number of operations will scale like an area of these free planes, not like a volume.
Okay, thanks.
Again, I can easily show you simple mathematics which will convince you that that's the case. So if you're interested, let me know. All right. So now what we do experimentally, we have this piece of equipment. We initialize it at some state. We run a cycle, we find a better state. We run another cycle, we don't find a better state. And then we run another cycle, we find a better state, and we keep going, find better and better state. And then the procedure seems to be trapped into some low energy state. At this moment, we stop running our cooling cycles. We record this state, its energy. So this is an energy in units where Jij is between plus minus 1. Right? So you have 5,000 qubits. Each one is coupled to 16 neighbors with a coupling which is roughly plus minus 1, in between plus and minus 1. And that's a typical energy of its, ground state, or low energy state. So we find the state with certain energy, we record the state, we record that energy, and then we start again from some random other state, and we again run cycles until we're trapped. And at that moment, we again record this state and record its energy and keep doing. So in the end of the day, we find the distribution function of many, many states. There are few thousand states, I believe, here. So they are energy distributed very much in a Gaussian way. We don't know why, but that's sort of experimental fact. Now, the simplest thing to do is to just pick the one which has the smallest energy and say that that's the best optimization outcome you can achieve. And it's pretty good, but you can actually do better if you do some statistical analysis of these states. So you can arrange them. So horizontal axis here is just all the low energy states which we found. There are a few thousand here. And the vertical axis is a distance between them. And the distance is measured by how many spins you have to flip to go from one state to another. So when you arrange them, and there is a very standard software which is called dendrogram, which allow you to arrange them in that kind of thing, you see that they can be sort of classified in different basins. So those are minimas. So the different colors here are the different minimas of this multidimensional energy landscape. Okay, so let's say all these brownish states, they are relatively close to each other, and they all have very small energy, but then they are somewhat isolated from the bluish state, or whatever, which occupy another energy minima, and so on and so forth. So you can arrange them in a pretty intelligent way and calculate how many basins you have and how many states in each basins, and how all of this scales with the distance. So again, I'm not going to any details. That just to sort of let you know that we have pretty detailed statistical understanding of those states. So once you do it, then you can do the following game. You can pick two low energy states you compare them. Let's say there are 500 spins which I need to flip to go from one state to another. I will look at these 500 spins which I need to flip, and I look them in real space on a lattice. And I will discover that they form few connected clusters, which are still disconnected from each other. So out of 500 spins, let's say I will have one cluster of 100 spins, a few clusters of 50 spins, and then even more clusters of, I don't know, 5, 10 spins, which are connected by non-zero Jijs. So since they are disconnected from each other, I have now freedom of, with my laptop, with my conventional computer, I don't need device anymore. I can flip them separately and see which of these flip give me best decrease energy in a most significant way.
So
yeah.
these clusters are precisely those spins which you mentioned earlier in the talk, which you need to flip to go from one local minimum to the other, right?
Yes, exactly. Yes. Those 55 spins, which is hard to find, here I can find by comparing two distant low energy states. And I will know which 55 spins I want to flip to go from one to another. Okay.
I'd like to ask one question here.
Sure. Absolutely.
So is identifying the clusters, does that have anything to do with the dendrogram that you've shown us in the previous slide?
Yes and no. Dendrogram, I need to have an idea how many distant minima I have.
And it looks like dendrogram does also conceal the energy levels. So it doesn't seem like there's a trivial relationship between distance, direction, and energy.
Absolutely. Absolutely. You are completely right. So all what dendrogram tells me is how many distant basins I should expect. Okay. Well, and again, I can do my dendrogram for different windows of energy. So I have thousands of low energy states, and I can separate them in energy direction. Let's say I will take 1,000, which is sitting in this window, 1,000, which is sitting in that window, and I will do dendrograms separately for each window. So then I will have an idea how many basins at what energy level statistically is there. Now, once I have this idea, I will more or less understand how many pairs I need to compare to cover all the different basins.
So identification of clusters, to me, seems like itself a very complicated problem.
No.
Am I wrong?
No. That's a very easy problem.
Okay.
That it's definitely, well, I don't know if how it scales with total system size. Probably just linearly. So no, it's not a computationally complicated thing.
Good.
Right. So once you identify the library, so you compare these clusters pairwise. Not clusters, take it back. You compare low energy states pairwise, and for each pair you identify clusters which you need to flip, and then you take another pair, you identify other clusters. So you create a whole library of these clusters, and then you start playing with them by flipping in a way to find new states which are better in energy than what you had before. And then you repeat this procedure with these new states, and you keep doing it. And it's by one reason or another, we don't quite understand why, it very fastly converges. and it converges to a single state. So this is an experiment for 1,000 spins. So we take certain number of low energy states, let's say here. We run this procedure, it converges to a state. Then we take completely independent set of low energy state, run this procedure, it converges to a state, which is exactly the same state. And then we do it many, many times. I think 25 here, or maybe 50, I don't remember. And it always converges to the same state. So there is no mathematical proof, but we very much believe that this state to which it converges is a true ground state.
Okay, can I ask one more question? It's very, very interesting, this story. So can I approach this with an RG ideology? So you're talking about clusters. So do they themselves behave like spins or some spin-like object? And now you're facing a smaller Ising cluster.
Absolutely. It's a very, very good question. It indeed smells very much like RG. So algorithmically, that's pretty much what we do. Now, how to make it analytic and what kind of theory one can extract out of this, I don't know. I thought about it, but I'm not smart enough to say anything. But as an algorithm, that's precisely what we do.
I mean, you can basically say that all of these states which are collapsing into a single state, this is an RG flow which is taking different states to the same fixed point. Maybe that's
yeah, of course, yes, it is. But how to make this statement predictive beyond just algorithm which works, I don't know. Maybe algorithm is good enough already. Maybe nobody needs sort of mathematical theory of it. Anyway, so the experimental observation is that if we do it, let's say for 1,000 spins, which is, technically I have 2 to the power 1,000 possible ground states, but nevertheless, in few seconds, so machine time is finding one state is microsecond. So in few seconds of machine time, I can find thousands of states. And then in another few seconds of running classical algorithm, I can converge to this single state, which we believe is a true ground state. So experimentally, in few seconds, for n equal thousands, we're pretty sure that we can find true ground state. Okay, now that's good, but so things become worse if you go to the maximal size, which we have 5,000. So here you need, everything scales again exponentially. So here you need many, many more experimental states because there are more Bayesians, as we know from the dendrogram. So we need more Bayesians. We need more pairs to compare. We need more clusters in our library. It doesn't converge in single step. There are a few generations. So we start from these blue states distributed around this energy. This is experimental results. Then we run first step of our RG, as you rightly call it. We come to the second generation of states centered here. And then we do it again. We come to not a single state. In this case, it's 2 states. Half of them come to this state and half of them converge to this state. So these 2 states are different by a single cluster of about 60 spin. We know precisely what's this cluster is. We want to believe that this lower part is a true ground state, but again, there is no mathematical proof. That takes, again, maybe not a few seconds, but about a minute or 2. And we believe we have very, very good candidate to find ground state of spin glass of that size. Now, how does it scales? I mean, what do we understand about scaling? So we understand that excess energy, right? So once we know true ground state, or we believe that we know true ground state, we can easily tell what was excess energy of experimentally found states, right? So this is my ground state. Now, blue states are experimental results, and they're Gaussian distributed, and I know that the center of this Gaussian is that much above the true ground state. So I know the typical excess energy per spin is a better thing, so I call it effective temperature. So excess energy per one spin, we can call effective temperature of this experimental ensemble of low energy states. Okay, it's of course not a true thermal ensemble. It's not uniformly covering entire phase space. Those are very specific states obtained by our cycling procedure. But roughly speaking, we call this excess energy effective temperature. Okay, I think it's sort of not a bad terminology, although not precise. So we know that this excess energy scales linearly with the system size, and that means that per spin it is a constant. So excess energy per spin is a constant. Yeah, and we know how it depends on how fast we do things. I can discuss it, but probably let me skip it. So the lessons from this part of the story is that effective temperature which we can achieve using this quantum device, whatever it is, we don't know exactly what is inside, but experimental result that effective temperature is less than 10 to the minus 3 in units where Jij is between plus and minus 1. Okay, so it's again, if you go back, so you see that the typical energy is 8,000 in this case, and the excess energy is what? About 15, right? So it's 15 out of 8,000. So that's a really, really very, very small energy. So if you think these states are extremely deep states, classical algorithm, which you can, model on your laptop, will typically give you this effective temperature 10 to the minus 2. I haven't seen any classical algorithm which give you better than 10 to the minus 2. So this device, again, whatever it is, quantum or classical, we don't know what it is, but this device easily gives you 10 to the minus 3, which is an order of magnitude improvement in sort of effective temperature of the ensemble. Now, if you
can I ask a provocative question here?
Sure, absolutely.
So 10 to the minus 2, and whether 10 to the minus 2 is good enough or you need 10 to the minus 5, it's entirely determined by an application. So it might very well be true that at 10 to the minus 2 we're good enough, and I don't want to spend $1 more million.
Absolutely. Absolutely. It all depends what sort of your customer want. If you want 10 to the minus 2 is good for you, fine.
So which application requires 10 to the minus 3?
Yeah, very good, very good. That's precisely what I'm trying to say here. So what you can show is that if you want to find a true ground state with, again, with certain probability, it's never mathematically exact statement, it's a probabilistic statement. So if you want to find a ground state, let's say with a probability 90%, right? Then you can show that using these algorithms, you will spend time which scales like 2 to the power effective temperature times n. Okay. So if n equal, I don't know, 5,000, and effective temperature is 10 to the minus 3, then it's not too bad. You can still hope to find true ground state. If effective temperature is 10 to the minus 2, then you're in a much worse shape. You have a factor of 10 in the exponent. You will spend much longer time finding a true ground state. But you're right. Maybe you don't need a true ground state. Maybe state with 10 to the minus 2 is good enough. Then you don't need quantum computer. Okay? That's one answer. Another part of the answer, which why D-Wave actually makes money, is because this is scaling, and we don't discuss what is sitting in front of the exponent. Okay? Now, with classical algorithm, even with effective temperature 10 to the minus 2, you will still spend hours finding those states. The D-Wave machine, as I said, in a microsecond can give you states with 10 to the minus 3. So the overall time scale already today is many, many orders of magnitude better. Okay. Now,
So
what
can
kind
we,
Mhm.
I mean, can we call this a direct demonstration of quantum advantage?
Well,
Or does it?
I would be careful.
Right, okay.
Now, first of all, machine is pretty lousy. Coherence times are not very good. So we don't know exactly why it is efficient in finding these states. Maybe because it's quantum, maybe because it's a, smart classical analog device. So I would be very careful about sort
Okay.
of claiming quantum advantage. But for sure, this is a device which solves this particular problem order of magnitude more efficient than any other device.
Right.
Okay? Quantum or classical, I don't know. Now, if you compare it with this mathematical statement, 2 to the power n to the power 2/3, then of course asymptotically, mathematicians are right. We say if n goes to infinity, this is always better than anything what device will give you. But on another hand, there is no, as far as I know, there is no any theoretical limitation how small this effective temperature can be. So as long as your number of qubits or number of spins is less than inverse effective temperature to the minus 3, this device will beat mathematical expectations.
Can I speculate that Heisenberg uncertainty eventually limits this through energy time principle?
Look, yes, but it's like third law of thermodynamics, right? Which tells you that you cannot reach zero temperature.
Yeah.
But it doesn't tell you how low it can be. Maybe 10 to the minus 6. Cold atom people say that they have 10 to the minus 8. Who knows, right? So, so I don't think there is any way to say T effective cannot be less than 10 to the minus 5. Maybe I can invent algorithm and I can invent device which will give me better. All right. So now, how much time do I still have?
Actually, we don't have a time limit, so we can
Okay, so
just as you
let me
wish.
try go to something a little bit more kind of exciting. Uh, so the next thing is to do kind of AI neural networks and image recognitions and things like that. So we started with Hopfield model, which was Nobel Prize of 2024. So there is this beautiful paper of Hopfield. He was thinking about functioning of the brain, but already back there he understood that it's actually maybe about computer algorithms more than about brain functioning. So in his model, which is not actually what is used today, but his original model was to construct to have certain number of images. P is the number of images. Each image has n pixel. Okay. And you want to store P images. So each image is a string, pixelated string of size n, which is called Xi. Now you form your Ising matrix of connection of Ising spins here in a very specific way. You form it out of this pre-recorded images. Okay. In a mathematical language, your Jij is n times n matrix of rank p, and p is much less than n. Okay. Now, what people understood after Hopfield is that if p is less than this magic number, then there is a pretty much one-to-one correspondence between deep minima of your spin glass and images which you recorded. If p is larger than this magic number, then this correspondence is broken, and minima do not have unique relation to this vector's Xi. Is it more or less clear, or am I too fast?
Yeah, it sounds clear.
Okay, very good. So then idea is this: we create this spin glass. Now you come with new image. It's a string, let's say sitting somewhere here. So you initialize your system in this image, which you sort of take a picture of it, and then you let your spin glass to evolve according to certain rules of evolution, and it will go to nearest minima. And you know that this nearest minima correspond to image number 2. And then you say, okay, so that the image I see is more or less what is called image number 2. So it's, I'll give you immediately example. So here are two images. We have Schrödinger cat and Schrödinger dog, which we sort of memorize using Hopfield algorithm. Now we come with initial state, which is a corrupted image. We do this procedure of quantum annealing. That's a real experiment. It's not it's not just pictures. So we start from state like this. We do quantum annealing by playing with magnetic fields. We come up with a state like this. And we start with another initial state which look like this. Again, we do quantum annealing. We end up with a state which looks like this. Okay, so that sort of demonstration for fun. Now the problem with it, specifically with the D-Wave computer, is that this matrix, which Hopfield wants you to create, it's actually all-to-all matrix. It has a small rank, but it's a full matrix. All elements of it is non-zero. And D-Wave machine allow you to have only very small percentage of Jij to be non-zero. Okay. As a result, we can never be any close to this theoretical estimate. So this theoretical estimate is for the full matrix Jij. Since we don't have a full matrix, we cannot store more than, actually, we cannot store more than 2 images, to be completely honest with you. So those are images 75 times 75 pixel, and 75 square is exactly 5,600. So that's precisely how many qubits we have. So each pixel here is just 1 qubit. Okay, and the problem is that our connectivity matrix Jij is very sparse. And as a result, we can just store two images, and that's not good at all. But for 2 images, it works beautifully. Okay, so then we went ahead. So again, as I said, today nobody use Hopfield kind of model. People realize that you should have this, better have this hierarchical layered neural networks. And that's actually much easier to implement on D-Wave hardware. So what we did, we created a simple neural network. It has input layer, which are pixels of those images. So those are standard images. There is a huge database called MNIST. It has hundreds of thousands, maybe millions of handwritten digits. So this is digit 7, 28 times 28 pixels. 28 square is 784. So those are input data for our neural network. So this input data is connected to a layer of neurons, which are qubits, and we took 120. And then there is output layer. So we have 40 for kind of error mitigation, but think about it as just 10 qubits in the output layer. So if you see configuration like this, everybody -1 and 1 qubit has +1, then you know that this digit is 7. Okay, this is 0, 1, 2, 3, 4, 5, 6, 7. So that's the idea. So you create your Ising model such that you come with an image which provides certain bias onto these neurons. You find the ground state of your Ising model. You look what are states of this output layer qubits or bits. And if you see something like this, you can confidently say that you see number 7. Is it clear?
Yeah, it sounds clear now.
All right. Okay, so mathematically, it's again pretty much Ising model. I use this instead of sigma z, I just use capital Z information notations. So the important thing is that this Ising model has many parameters. So those are vectors and matrices, which should be sort of trained. You should train your neural network to have the best values for all these Jij and magnetic fields and W metrics. So W metrics, I believe, is connections between output layer and the hidden layer, and those are connections between hidden layer and output layer, and so on and so forth. So you don't know in advance what are these parameters. So to know this, you want to train your neural network. Now, how do you train it? You present it with images where you do know the answer. So again, I give this image and I do know that it is 7. So I do know that I want to see this output layer like this. So I create a bias to tell my Ising model that those spins should look like this. And then I find a low energy state of this model. And depending So, and then I change the parameters. So I start with some, let's say, I will show you pictures in a sec. I start from random values for always W, J's, B's, whatever. And then depending on what energy states I find, low energy states I find, I incrementally change them a little bit. Then I give it another image, find low energy state, incrementally change it a little bit, and keep doing it many, many, many times. Now that looks approximately like this. So this is a training a dragon. So those images are projections of my multi-dimensional phase space or configuration space into two-dimensional plane. And this projection more or less preserve, not 100%, but preserve coming distance. So how many, so the geometrical distance between points, so each point is a low energy state, and the distance between 2 points more or less represent how many spins I need to flip to go from one to another. Okay, that's the idea, is just to visualize what we have. So we start from completely untrained neural network, and its low energy space is a complete mess. It's a total spin glass. There is no order at all. And then we start running this iterative procedure, changing parameters step by step. And what you see is that some order emerges, and eventually it's all the state separates into 10 basins. Each basin here represents a certain digit. So the color of the state is chosen according to position of output layer. So if it's, let's say, orange, then it means that it's 1. Right? If it's blue, then it is digit 0. So what you see is that while doing this training, your system undergoes basically a phase transition from a glass state to an ordered state. Okay, so in ordered state, I have just 10 low energy basins, and each basin is responsible for 1 digit, recognizing 1 digit. In initial state, I don't have any basins. It's a complete mess. And in the middle, you see it kind of evolve from the mess into ordered state. Okay.
Sir, can I just interrupt here? What
Yes.
do you mean by order? For example, some paramagnetic, ferromagnetic, or something, or just shape like order?
Yeah, look, you can call it sort of a ferromagnet, right? But it's not a simple ferromagnet which has just 2 states, all up or all down. Okay, this is a ferromagnet where my Jijs are such that it has 10 minima. Okay, they are relatively distantly far away. If you want to go from one minima to another, you need to flip order n spins. Okay, but it has only 10 minima, and each minima has a very definite configuration of output spins, like those. Everybody -1, and one of them is +1. Okay, so call it ferromagnet, but it's a little bit more intelligent ferromagnet than just everybody up and everybody down.
Okay, thank you.
Does it explain?
Yeah, exactly.
Very good. Yeah. So, and what you start from is a glass. So in a sense, it's a transition between glass and quote-unquote ferromagnet. Okay? And I think it's a sort of generic idea behind any neural network or AI training procedure that you want to pass this transition. Okay, so here is it slightly more details. So here I present always digit 7, and I look what kind of low energy states I measure. And if what I measure correspond to 7, it's this magenta color. If I measure something else, it's different colors. So you see that if it's poorly trained neural network, then yes, in most cases I do see 7, but sometimes it's not 7, sometimes it's something else. If I present this now and I measure low energy states, again, sometimes it's 7, but in most cases it happened to be not 7. It's actually, what is it? 9. In most cases it thinks that it is 9. And so on and so forth. But once I do sufficiently many training cycles, and again I present the same image, and I measure low energy states, all of them tell me, yes, it is 7. Okay? No, okay, so now why this D-wave machine is good? As I told you, it can sample in no time, in microseconds. It can sample many, many states, low energy states. So instead of having just one low energy state, I can almost for free, practically for free, in no time, I can have thousands of these low energy states. And you can use this knowledge to accelerate your training, since you at once you can sample many, many, many low energy states. Now you can say, okay, let me try to use it. So we use it in a sort of pretty naive way. For each change of the parameters, we have basically kind of algebraic mean of all those states. M is a number of low energy states which we measure. And we use very naive training rules. But already with these very naive training rules, we see that our training rate is much better than classical analog. So what is plotted here is error, fidelity of my image recognition, how often I make an error. And you want this number to be as small as possible, of course. And it plotted as a number of epoch, and epoch is one cycle of presenting all of your training images. Let's say in our case, I think we have 100,000 training images. So one epoch is presenting 100,000 training images once. And when we do it for the second time, it's a second epoch. When we do it third time. So altogether we did it here, I believe 13 times or 12 times. I forgot how many times we did it. And you measure error rate of your image recognition. And you see that with quantum device, it goes down much faster than with traditional ways of training neural network. But that's a very, very kind of primitive way of using this quantum advantage. So we understand that there are much better way of doing it, which based on kind of variance of a Groover algorithm, which is known as amplitude amplification algorithm. It's 20 years old. People know about this these things for quite a while. I don't think they ever thought about using it for training neural networks, but it's sort of pretty straightforward idea that if this quantum advantage is indeed working, then you can do it actually much better. So how much better? So here, if you look on an inset, the least exponent. So this is a logarithmic plot, and scaling exponent is a slope of these straight lines. So what we currently have is a slope -1, which is sort of better than what classical algorithms are giving you. Now, if you can use this quantum amplification, we understand that it can be easily, not easily, but it can go all the way up to 2. So you can double the scaling exponent. So instead of having power -1, you will have line which go with a slope -2, which will be much, much faster than what classical algorithms have. Now, we're currently trying to check if it works or not. It's not easy. It requires quite a bit of work, but there is a sort of clear way of doing it. So we're hopeful that maybe not all the way up to 2, but I don't know, 1.5, we can achieve with better algorithms. Same device, but just using better algorithm, better protocols running this device, we can make it even faster, right? So that probably brings me to conclusion that I believe that if quantum computers will be good for anything at all, it will be good for training of AI algorithms. Now, it's not easy because we know how much money and how much, effort and brain goes into classical training of AI. So truly beating them and demonstrating advantage of quantum computers will not be easy, but I think it's still possible and it's promising. And I think it's much more promising than thinking that factorization or cryptography or any other popular application of quantum computing, which you can read of. I think AI is truly true arena where quantum computations may be good for. And that's probably all what I have. So those are my students who did all this. They already all left. And yes, thank you.
Thank you for the great talk. We may have some couple of questions. If there are any. I think no one has. Actually, I have one question. Actually, I just took a note about your dendrogram stuff. So actually, I wonder whether can we just diagnose a phase according to this dendrogram? For example, paramagnetic, because the glassy transition is subtle, can we understand a paramagnet and spin glass apart from this dendrogram graph?
By paramagnet, you mean in presence of magnetic field?
It don't have to, I think.
So what is a paramagnet?
So, for example, I just took a long time average, and it don't have some magnetic property, but it has some random spins, align spins, which has a non-zero overlap. Pardon, sorry, zero overlap.
Look, again, I'm not sure. So phase transition is function of what? I mean, what drives you between glass and paramagnet?
It's overlap function, maybe.
Yeah, overlap function is a diagnostic, but what do you change physically to go from one to another?
Temperature might do.
Temperature. Okay, fine.
Size of the model.
Well, dendrogram characterize low energy or whatever states in a certain energy window, right? So if somebody give you so many states and tell you that they all belong to certain energy window, you can plot your dendrogram, right? So if it is a glass, then you see so that many basins, and we more or less know how many of them we should expect. If you take a high energy, meaning high temperature, and you plot the same dendrogram, would you be able to see it that it is not a glass but a paramagnet? Probably yes, but I don't know quantitatively how to do this analysis.
Okay, thank you.
Can I ask two short questions? So,
Absolutely.
what is about this neural network? So, are we considering a conventional neural network with nonlinear activation functions, or are you writing a cost function in the Kubo form that you can easily solve with annealer?
Well, probably the second. I mean, it's for a given stage of your training procedure, your neural network is nothing else but Ising model.
You mean the Ising spins are actually the coefficient, the parameters of them?
Yes. So I choose some parameters Jij and magnetic fields and whatnot, but it's in the end of the day Ising model with certain external magnetic fields applied
So
locally.
I don't see how it works if activation functions are nonlinear. I can certainly understand that perceptron is linear device that can be represented in terms of a Kubo problem. But I'm missing something about how with nonlinear activation function, the cost function can be written in Ising form.
Well, you mean more than two spins, products of more than two spins in a cost function?
So, for example, I write cost function of a multi-layer neural network, then there will be cascaded nonlinear functions. So these ReLU or whatever activation function you use, there will be a chain of them composed together. And it doesn't look like you can write it in a quadratic form in that situation.
Well, no, I think you can. I mean, so if you have a layered neural network, then all what you have are connections, quadratic connections between neurons in adjacent layers.
But if you have nth layer and the first layer,
yes,
then there is a composition of nonlinear functions between the first and the nth.
Yeah. I mean, if you want to sort of eliminate all intermediate layers and look what's connection between initial and final, then it is a complicated function, which I don't know what it is, of course. But microscopically, that's what I built using my machine. is just connections between successive layers, and they are linear, they're quadratic connections between just neurons in this layer and in the next layer, and then next and next. Okay, so I built this simple neural network, nothing fancy, and then I'm looking for low energy states of the entire network. Okay, and what I'm concerned is I take one of those low energy states and I specifically look for output layer, and I look whether those spins are up or down, and that give me information what image I see.
Okay, I'll think about this.
Okay.
Maybe I'm still missing something. My other question is about how. So to what degree are we certain that quantum mechanics is pulling the actual weights in the D-Wave device? I think this has been a controversy, but I just want your point of view.
Well, yeah, that's a very good question, and I think the answer is nobody quite know to what degree this device is quantum or classical, and it's not easy to actually quantify it precisely. So each qubit is more or less, I mean, we're pretty much sure that each individual qubit is fully quantum mechanical. It's sort of three-dimensional magnet. Now, let's say I take two qubits. Is there mutual coherence between them? To some extent, probably yes. Now I take 10 qubits. Do I have fully coherent states of 10 qubits? Probably not, right? So they are sort of individually coherent, pairwise maybe they are coherent, maybe 3 of them are to some degree coherent. But if I take 10 of them, probably I don't have full entanglement at all. But I'm just throwing numbers. It's not easy, neither theoretically nor experimentally, to measure it.
But also there's definition issue, it's a semantic issue. Let's say I have a big protein and it falls. It's a massive optimization problem, and protein solves it in nature. Protein is made up of atoms and it's quantum mechanical object. But is folding of protein is a classical process, or can we call it a quantum process?
Well, look, that takes me too far away. I don't know. At least it is an open quantum system, because you have, besides of your protein, you have plenty of stuff around, right? Water,
yeah,
salt, whatnot. So it's never truly quantum problem. It's at best what we call open quantum system, right? Reduced density matrix. But how much coherence is in this reduced density matrix, nobody knows.
Okay. Thank you.
Okay, if there are no other questions, we can stop recording, and thank you for the great talk, sir.
Thank you.
For this insightful talk.